This discussion is all really about the how of plate tectonics. We've talked a lot about evidence for plate tectonics, right? We saw Wegener's evidence for continents, coastlines, fossils, and climate. And then we also added some seafloor evidence about the age of the rock, the sediment, and also the magnetics. However, we have yet to explain really how the continents are moving or what's creating them. And so we're going to get into the Earth today and kind of figure out what's going on there to make our crust move on top. We do that, we have a few essential questions to think about. We want to know really what a convection current is and what are the forces it creates. And there's two main forces that we're going to look at with these convection currents. One of them is called slab pull, and one of them is called ridge push. We'll be looking at those two different forces and seeing, well, which type of boundary do those match up to. And so that'll be kind of our focus for today. So to start out, let's make sure we list out what those three forces are that make plate motion. And again, like we said, this is really the how of plate tectonics that Wegener could not explain. Okay, this is the how the plates are actually moving. We see all the evidence, but we want to make sure we know how plates are moving. So we'll talk about convection currents happening inside the Earth, and then these two are forces that occur because of that convection current. So let's make sure we really know what convection currents are, because we've actually talked about them quite a bit in other units, like our climate, lame cow unit, but we haven't officially given them that name yet. Convection currents. Convection is when we have circulation of any kind of material due to a change in density. And so what we talked about with lame cow is when we have things that are more dense, we see them tend to sink, while things that are less dense tend to rise. And so we actually see this happening inside of the Earth in our layer asthenosphere, which is the top part of the mantle. And we kind of use an analogy of a conveyor belt, because what we're seeing happen here inside the Earth is that as this convection occurs and we have material rising up in the asthenosphere, well, our thin layer of lithosphere is affected because of the movement underneath. And so kind of like a conveyor belt, anything that moves underneath is also going to move that layer above it. So if you think about like at the grocery store, when you put your groceries on that conveyor belt at the register, right, your bottle of pop or your jug of milk, whatever it is, because the conveyor belt moves, that object also moves. Or even another analogy of like floating on something. So we have water, which would be like the asthenosphere, and then a little boat hanging out on the water. The current of the water drives the motion of the boat. So that lithospheric crust, that solid rigid layer, can't move unless the asthenosphere layer is moving underneath. So we have a nice visual here of what's happening inside the asthenosphere and how that motion is directly correlated to the motion of the crust. So we see the swirling and the movement of that material in the mantle because of density changes, and then we see some arrows showing up here on the crust showing the movement of that material, again because of the movement of this material underneath. So let's think about, on the right-hand side there, other areas on Earth where convection is happening. And we talked a lot about this in our lame cow or our climate unit, seeing this happen both in the air and the atmosphere or the ocean or water. Both of those materials are able to quickly change density and therefore move or have a flow to them because of those changes. So we see here some global winds are happening because of convection, right? We have warm rising here at the equator, sinking here at the poles. We have local winds, where we see a mini version of the global wind idea, and then here's our ocean currents, again heated by the equator. Now all these things here have one major heat source, and that of course is the sun. Okay, but when we're thinking about our convection inside the Earth, the sun is not able to provide heat to those lower internal layers. So our heat source has to be coming from elsewhere. All right, so we have a heat source coming in, creating hot mantle material, and we know from previous discussions that hot material has a lower density and therefore will rise upward. So we want to label on our diagram here the warmer rising material down here inside the earth. And so let's get some arrows in there. I'm using a red pen. That would be a nice visual reminder that that is the warmer, less dense material. Now that material can't stay that warm forever. It's getting away from its heat source and eventually will cool down, becoming more dense and then sinking. And so that entire flow or that process is known as the convection current. So here we have the cooling of the material. And that, like we said, is the more dense. So there is our entire flow of the convection current. We've got some kind of heat source down here inside the earth, heating up the material, causing it to rise, reach the underneath part of the crust and kind of separate there, and then cool as it's further away, reheated, and continually cycle through for our idea of convection. So what is that heat source? Where is the heat coming from? Well, if we look at our diagram here, we see our convection currents happening here in the asthenosphere, and the heat has to be coming from this lower source. We know there is an immense amount of heat happening inside of the earth, and it's happening there because of all this radioactive material inside of the earth's core. So that hot material drives this convection current, causing the warm to rise and then eventually causing the cool to sink. And it's important that we note that this warm and cool, they're still thousands of degrees. It's just cooler here relative to the warm that's rising upwards. And that motion inside the earth creates then this movement here that we see on top, like the conveyor belt or like the boat on the water. So let's make a connection here. How really does convection cause plate tectonics? Well, we know that inside the earth we have the asthenosphere, and that asthenosphere has the flow to it, where we see warm material rising up and cool material sinking down. And so the movement of that material inside the earth causes movement of the crust on the top. And so we can't move on the surface unless we have movement and motion underneath. So give your own words a little explanation there in the summary section, and then see if you can think back and add in one of those analogies that we gave. What did we say the asthenosphere and the lithosphere were like when they moved? So because we have the motion of the convection inside the earth, we see the same motion on the surface of the earth. And that motion then is connected to two forces or processes happening on the earth's surface. This section of convection is directly related to a force ridge push, while this section of the convection is directly related to a force slab pull. So we want to investigate a little bit further what this ridge push and slab pull are, what kind of boundaries and features we then see at those locations. Ridge push is directly related to the part of convection that has rising mantle material. As that mantle material rises up and hits the underneath of the crust, it pushes and separates underneath the crust. And because we have that separating motion underneath the crust, we see then the actual crust moving in that same way. That force then created is called ridge push. Now it creates a major feature here called the mid-ocean ridge, which has a higher elevation, and so gravity also plays a role in pulling those rocks down and away from the ridge. Being at a higher elevation, we know gravity plays a role and pulls material down. So it works together with the convection inside the earth to create ridge push. A few major features associated with ridge push are the mid-ocean ridge and the Rift Valley. Mid-ocean ridge we've talked a lot about, and we know that is located in the middle of the ocean, but it's a pretty big feature. It's the entire elevated area where magma is coming up around that boundary. So this entire area we want to make sure we label as the mid-ocean ridge. The Rift Valley is part of the mid-ocean ridge, but it's actually right between the two plates. So it's in the middle of the mid-ocean ridge, the location where the actual new crust is coming up. Because remember, what's happening here is my convection underneath rises, pushes magma out of that Rift Valley, and then the rest separates underneath the crust, causing the lithosphere to move in that same way. This, again, is known as a divergent boundary, a location where the plates separate relative to each other. Just a visual here of what these look like in real life. We have here the ocean-ocean divergent boundary where the plates are moving apart due to convection inside the Earth. Again, we have the mid-ocean ridge, this entire elevated range around the Rift Valley where the actual magma comes up. This one here is two pieces of continental crust, no mid-ocean ridge here because we don't have the ocean, just simply the Rift Valley where the magma comes up. The plates are still separating, and over time this Rift Valley can become big enough to be a water-bearing location. Second force created by convection is slab pull. Slab pull occurs more where the convection is sinking due to cooler, more dense material. As it sinks, it takes this older, more dense crust with it. And so we call this location here slab pull. Again, gravity does play a role in this force. Due to the density and heaviness of this plate, gravity continues aiding the pull downward. Common features found at a slab pull location are subduction zone and trench. Subduction zone is where we see the old plate being pulled down into the earth, and once it reaches far enough into the earth, we know that the heat increases and we see that plate really melted and recycled back into the mantle so it can be reused. Trench is the deep area, most importantly, between the two plates, wherever subduction is occurring. So if we're looking at our diagram here, again, remember slab pull is happening because of the cool sinking material. And so this area right here, that is the subduction zone. And the trench is right where those two plates meet. Those are common areas at slab pull. Again, gravity plays a partial role in helping pull that old dense plate downward. Another visual here of our slab pull. Due to that sinking convection material, this old plate is pulled downward. We see lots of earthquakes happen as we go, but the main thing to recognize is as it gets far enough down, melting occurs, causing magma to rise to the surface, creating volcanoes on the surface. Now that our discussion is complete, be sure you go back and answer those essential questions 1 through 5. And there will be a slide next just with a review here that you could practice, pause, and see if you can label all those locations.